Hello again, class. Today we're going to be looking at section 8.5. I'll be assigning that today, April 8. Because we don't have class on Friday, this one will not be due until next week, Wednesday, April 15. So section 8.5, assigned today, due on April 15. I need to tell you today's lesson is not super long, but it is one of the more challenging lessons from a pure algebra point of view. So kind of get ready to go pretty hard here for just a little while. I'm going to start off easy. We've had addition of like terms in algebra. We've had that for quite a while. An example would be 3x plus 7x equals 10x, where we add the coefficients. Well, x, always remember, can stand for anything. So if I have another variable, y, that implies something else. So here the 3x and the negative 8x are like terms. They can be added together to give a negative 5x. But the 5y has to stay by itself. The x terms were like terms, the y term was not. Well, as we mentioned, you can put a lot of different things in there. But we also can have powers here. Like terms would be these two. They're both x squared terms. So 3 plus the 5 gives me 8x squared that you see right there. I have a 8x cubed. There's no other x cubed. There's a y cubed, but not an x cubed. So the 8x cubed goes by itself. I have 2y to the fourth. So those two, I add the coefficients. 4 plus 7 gives me 11y to the fourth. And I have this y cubed, 6y cubed term all by itself. So I can add some terms when they're like terms. Others, we cannot. Now, just like we added up here at the very beginning, 3x plus 7x equals 10, the x could be anything. In this case, I let the x be radical 5s. They're the same as something here for x, radical 5 in both cases. So here, just like we added the 3 plus the 7 to get 10, I'm going to add the 3 plus the 7 to get 10. But notice I didn't go x and x to get 2x there. The x's just came along. So the radical 5 would just come along. Common mistake would be people would have said 5 plus 5 gives me a 10 in there underneath the radical, but it stays as a 5, just like this x stays exactly the way it was. Radical 5 stays exactly the way it was. Super crucial that you have a good understanding of this principle right there, because otherwise there's going to be a lot of confusion throughout our lesson today. Pretty important concept. This radical is not radical 10. Stays the same. Likewise, if I have one term that's not a like term, I've got to leave that one separate. For example, here notice I got two radical 11s. That's just like the two x's. They're radical 11s. So the two x's, I added the coefficients. 3 and negative 5 gives you a negative. 3 and negative 8 gives you a negative 5. So here this 3 and the negative 8 gives me the negative 5. The radical 11 just comes straight along. The radical 7, just like 5y was kind of out there by itself, 5 radical 7 is out there by itself, just comes along. Again, go through this one a few times. Make sure that you are very comfortable with the algebraic rule behind those. Some more examples. Notice this time, I not only went from two different arguments, 6 and 8, but I also went with two different types of roots. A cube root of 6 has to be connected with the cube root of 6. it cannot be connected with the fourth root of 8. So I have these two right here. It would be like a 5x and a 9x here. That would give you a 14x. So this one, 5 plus 9 will give you a 14 radical or cube root of 6. These two radicals are exactly alike. That would be something like 7y plus 8y. We can add those together to get 15y. So I would add these two together to get 15 times the fourth root of 8. And that becomes our answer. 14x, but it was 14 times the cube root of 6. 15y was 15 times the fourth root of 8. Again, a little bit messier, but the concept is still the same. Look for ones now that are exactly the same. For example, let's underline these ones. Fifth root of 3, fifth root of 4 is not the same. Fifth root of 3 is. This one and this one are like terms. So 11 minus 14 would be a negative 3 fifth root of x to the third. The fifth root of x to the fourth has another one of those right over there. So those two are like terms, which means I can add those coefficients to get a negative 27. And I have that fifth root of x to the fourth that tails along. This one right here, there is no match for it. Consequently, it just comes along as a negative 13 sixth root of x cubed. And that's why we ended up with that answer. Again, concept no more difficult than this up here, but it just gets a lot messier. In the last section, we looked at this algebraic rule. These arguments can be multiplied. So if I were to have this one right here, I would multiply my coefficients, 5 times 3 to get 15. And now because they're both fourth roots, just like both square roots here, I can take the arguments and multiply, but notice it's still a square root. So mine will still be a fourth root. 7 times 6 is 42. Again, the same principle. Algebra follows rules all the time. And as you can see, we got the answer there. Okay, this one. You'll notice that I'm not adding like I was up here. I'm multiplying. But I can only multiply when I have the same type of root. For example, cube root can be multiplied times this cube root. Like square root was multiplied times square root, and we multiplied the argument, 7 times that. So in these, I'm going to have to multiply the x times the z. The cube root will come along. So I have 4 times 6, which is 24. I still have the cube root, but I multiply the arguments just like 7 times 6 gave me 42. This is going to be x times y. Excuse me, x times z. I apologize. Let me rewrite that. X times z. This one is a fourth root. If it was a third root, it could have been combined, but a fourth root is something different that needs to stay by itself. Giving me that answer. And I'm guessing your book would have gone one more step. They would have taken 24 times 5 and got 120, and then put the radicals, cube root of xz times the fourth root of y. These again get to be kind of messy. Don't be afraid to rewind the video, go through it multiple times. Again, we're going to look at a fairly familiar principle, FOIL, but we're going to look at it with radicals. First of all, you remember FOIL. I had two binomials. I multiplied the first term. That was f for first term. So the two first terms were x and x, giving me x squared. O stood for outer terms. Outer terms are x and 7, so I multiply and we get 7x. I stood for inner, so the inside terms are 3 and x. And L stands for the last terms of each binomial. 3 times 7 gives you 21. We were able to add these like terms. Sometimes you can add them, sometimes not, to get 10x. But now you can see, rather than an x, I've got a radical. The FOIL procedure is still the same. So I'm going to begin by taking radical 7, multiply it times 5, radical 7. So 1 times 5 would be 5, radical 49. It's eventually going to be 5 times 7, or 35. Then I'm going to multiply the outer terms. That's going to be just simply 6 radical 7. The inner terms, 4 times 5, will be 20 radical 7. And the last term would be 24. But notice the first one here, I was able to reduce it down. So I got radical 49. That's radical 7 times 5 radical 7 gives you 5 radical 49. Do you see that these two are like terms? They can be added together. 6 plus 20 gives you 26, just like 7 plus 3 up here gave me 10. 6 plus 20 gives me 26. But now also the 24 and the 5 times 7, there's no radicals in those, so 35 can be added to 24, giving me my final answer, 59 plus 26 radical 7. That's an example of a FOIL distribution. This one is really no different. They're all square roots. So when I go the first term, times the first term, I get radical. 3 times 3 is 9 xy. The outer terms, I'm going to have a negative radical. 3x times 2x is 6x squared. The inner term is going to also be a negative radical. 2 times 3 is 6, x times y. Finally, the last term, a negative times a negative is a positive. 2 times 2 gives me radical 4. X times x is x squared. Well, in this case, I had these 4 terms. This one cannot be changed other than a 3 radical xy. This one I can go radical 6, remember absolute value because it's an even root. This one cannot be changed, it cannot be combined here. I shouldn't say that, I guess it can be combined, no. It cannot, it's not the same. So I have to leave that one as radical 6xy. This one finally can be 2 absolute value of x. And that becomes my answer. We've already done some work with rationalizing denominators. You remember, I could multiply this one by radical 7 over radical 7, which is a 1. That would give me 5 radical 21, 4 radical 49, gives me 5 radical 21. 4 times 7 would be 28. We've done that before, giving us that answer. Our last concept is we're going to look at rationalizing a denominator, but the denominator is not a single term like it was right here. Rather, it's going to be a binomial. Binomial means two terms that are either added or subtracted. This may not seem like a super important concept, but in upper mathematics, this one is used a lot. We need to multiply by a 1 here. The numerator and the denominator have to be the same. We choose a very special numerator and denominator. It's so special, it's actually given a name called conjugate. Conjugate means if I have a binomial, I simply switch only the middle sign. So rather than that middle sign being plus, I make it a negative. That's in the denominator. It must be the exact same in the numerator. The reason we chose that number, that expression, is because it will eliminate our radicals in the denominator. We're going to be rationalizing the denominator because notice my denominator is now a FOIL. So when I FOIL this out, I get 4 times 4, which is 16. 4 times a negative radical 3. To write that a little better, excuse me. Minus 4 radical 3. The inside terms are plus 4 radical 3. And the last term, radical 3 times a negative radical 3 is a negative radical 9. I'll get the numerator in a moment, but I'd like you to see the denominator. Notice these two terms in the middle cancel out. That always happens when you multiply by conjugate. This is 16 minus 3 leaves you 13. Notice my denominator no longer has a radical in it. The numerator is 5 times 4 and 5 times the radical, giving me 20 minus 5 radical 3. But again, notice when you multiply by the conjugate, you end up with basically the two squared terms on the outside. And because of that, you always get rid of the radicals. That's why we call that rationalizing the denominator. Okay? And this again just shows you the same process right there. Don't be afraid to hit pause on your video, walk yourself through each of these. That's called multiplying by the conjugate. A lot of people, this is the wrong way, hence wrong. A lot of people might have started with our first one, and they would have thought multiply by radical 3. Well, that would have gotten rid of that radical there, but notice it would have made a new one by the 4. And we would have still had a radical in the denominator. We did not reduce it. That's why it was the wrong way. We had to multiply by the conjugate. Same concept here. I need to multiply by the conjugate. I start with this. It's a binomial denominator. Happens to have 2 radicals in them. Doesn't matter as long as I multiply by the conjugate. The conjugate, you remember, is I switch only this middle sign. Leave everything else the same. In other words, I leave these two the same, but I switch this negative to a positive. That's a conjugate of that. That's why we say multiply by the conjugate. If that's in the denominator, I need to put it in the numerator so that the entire fraction is still 1. Then I'm going to do the denominator first. Radical 3 times radical 3 is radical 9. Radical 3 times radical 7 is radical 21. Negative radical 7 times radical 3 is a negative radical 21. Negative radical 7 times a positive radical 7 is a negative radical 49. Notice this plus radical 21 and minus 1, they cancel out. And you're going to be left with 3 minus 7, which is a negative 4, no longer a radical. The numerator is 5 times radical 3, 5 times radical 7. And that is considered to be reduced down. I'd like you to try that one on your own. I'll give you a head start, and then I'll follow you up. As I mentioned, this is kind of a short lesson. I am assigning here now section 8.5, assigning it this Wednesday, April 8. Because there's no class on Friday, it'll be due next Wednesday, April 15. Have a blessed Easter.